where currently he is in charge of the department, research analysis department, mainly focusing on different aspects of chromatography, including high temperature HPLC and miniaturization separation techniques. And he has presented in numerous conferences on the combination of LC and LC in the analysis of environmental samples. And I'd like now to pass over the presentation to Torsten. All yours, Torsten. Thank you very much.
Thank you, Steve, for this very kind introduction. Good morning, good afternoon, everyone. So this is about the LC times LC approach we have used and developed the last years, and I would like to share the results. So first of all, we have to answer the question, why do we need two-dimensional liquid chromatography? Well, as you might experience, the samples we have to analyze are getting more and more complex. What you see here now is a UHPLC TOF MS hyphenation chromatogram. And what you can easily see is that over the whole chromatogram there are many, many peaks co-eluting. So the problem is, if you would like to separate one compound from the other, it is not sufficient to use another phase system, so to use another stationary phase, another mobile phase. So we need another strategy. And one of these strategies clearly is to use two-dimensional liquid chromatography and to use methods with higher peak capacities. Now, if it comes to two-dimensional liquid chromatography, there are two techniques. So the first one is very easy. So it's just hard cutting, everyone might know. So if you are interested in this sample, you cut out this fraction and transfer this fraction to another column with another selectivity to obtain a better separation of these co-eluting compounds you see here. Okay, but this is not what I'm talking about today. So the other approach is applying comprehensive LC times LC. And here to show that the whole eluate will be transferred to the second dimension column. And as you can see here in this animation, you fractionate your whole chromatogram in different samples. These samples will then be reanalyzed online on a second dimension column. I will come back to this later, which is called the modulation process. Unfortunately, there are some known barriers of online LC times LC which have prevented this technique to become routinely used in, let's say, environmental or food laboratories. So first of all, there is this issue with the compatibility of the solvent systems. Now, you would like to use some orthogonal separation mechanisms. Many authors have used systems which are consisting of normal phase and reversed phase in the first and second dimension. Unfortunately, you use very different solvent systems, and problem is that you will observe peak broadening or even distortion by the solvent effects. So this is a great problem. Then we have the modulation. Modulation is always accompanied with a dilution, so you lose sensitivity. Another aspect is that you need to be really fast in the second dimension separation. And in order to achieve this, many authors used very high flow rates, up to, let's say, 5 milliliter per minute. Well, and this is not that compatible with MS detection, especially if you use electrospray ionization. So in this case, often split systems are used, but they will give you a lower reproducibility. And this was clearly the motivation for us to use a miniaturized approach where we used nano and capillary LC in the first and second dimension. What you see here is originally the development platform we used. It is the Eksigent Ultra 2D system, and it's really a nice system. I've given some features here. What you see here is the oven compartment, which can be heated up to 80 degrees. You also see here the two 10-port switching valves, and all in all, the system is very, very compact in its design to really get rid of dead volumes, which are detrimental to reduce if you're using micro LC. Moreover, there are two independently programmable gradient pumps, and you can exchange the flow modules to use the whole flow rate range between 50 nanoliters per minute and 200 microliters per minute without any split. So that's some great prerequisites. Okay, so one of the major features to really achieve very fast separations in the second dimension is the low gradient delay volume. And this is just 1 microliter. And therefore, very fast re-equilibration is feasible after a solvent gradient I will show you next. So this might be a little bit confusing at the beginning. What is plotted here is on the y-axis the time for the gradient from the time of mixing the solvents until it reaches the column head. So please know that this is a logarithmic scale, and on the x-axis there is the flow rate, which is given in microliter per minute. Now, if we, what you also see here is I've plotted 3 different dwell volumes. So this is for our micro LC separation. It's 1 microliter. The red one is, I would say, the best UHPLC systems, conventional UHPLC systems which are on the market have a dwell volume of about 50 microliter, and if you are using some older HPLC systems, the dwell volume might be up to 500 microliters. Okay, if I now adjust a flow rate of about, let's say, 50 microliter per minute, which is very typical for our kind of application, and I now use a system, I would call it one of the best UHPLC systems, I have a gradient delay time of about 1 minute. So this is too slow for our kind of application. Therefore, if I use our system at the same flow rate with just 1 microliter of delay volume, the delay time is in the order of 0.02 minutes, so just a few seconds. And therefore, very fast re-equilibration cycles are possible. Now, what you here see is also related to the separation speed in second dimension. What you see here is that very fast gradients can be programmed, and the system also reacts very fast after the end of the solvent gradient with only a minimal re-equilibration time. So this is really a prerequisite we need. Okay, on this slide I will show you the modulation scheme, the flow scheme. Actually on PowerPoint it's very, very easy. It's based on the two-loop technique. So how it is working. So first of all, you have your first dimension column. In this case, we use a nano column. And the solvent, the effluent, which is continuously coming out of this column, is collected here in this loop. So here we have the 10-port 2-position switching valve. Simultaneously, the other loop, the red one here, is connected to the micro LC pump, and this volume is then transferred to the second dimension column where the separation is achieved. Okay, after the modulation time, which is in the order of 1 minute, the valve is switched, and now it's just the other way around. So this loop will now be used for collecting one fraction, while the other loop is now connected to the micro LC pump, where the separation will then be performed on the second dimension column. And now we can switch forth and back until the complete chromatogram is fractionated, as I've shown you before, and every fraction is online chromatographed. Okay, on the next slide I show you the system volumes. I will not go through it and read everything out, but to show you that this was really demanding. So if you use such columns with low internal diameters, it is essential to minimize every dead volume. Otherwise, we will not be able to have a very good separation at the end. Okay, here's a picture which shows the system, which is on top of the triple top instrument from AB Sykes. And what is really important is that at the column outlet, you have to make a very short connection to the easy source. Well, there is one great invention which is made by AB Sykes, because you have to avoid or minimize the band broadening after the second dimension column. So you have to adjust the idea of the transfer capillary and the emitter tip to 50 micrometer. And this was possible because, as you can see here, it is easily possible to just exchange these emitter tips and then insert them in the normal probe. And for some nano applications, you could also use the 25 micrometer ID tips, but for our applications, the 50 micrometer ID tips were just perfect. Okay, so I will now go to the method parameters and explain to you how the system was built up. So in the first dimension, we used this nano column. We used a column from thermal hypercarb. It's made up of porous graphitic carbon. It's very retentive. That will be very important. I will come back later to this. The inner diameter of this column is just 100 micrometer. In the second dimension, we have the capillary LC column. We used a core shell material based on classical silica C18 with an internal diameter of 300 micrometers, so which is very typical for micro LC applications. Okay, what you see here is just a comparison between the PGC and the classical silica C18 material. So porous graphitic carbon is very well suited to retain extremely polar compounds. And this is very important for us because we are working in the environmental business, and small polar compounds become of ever more importance. And also it is possible to make a large volume injection on this column, which is necessary to really obtain a signal in this dimension. So moreover, PGC has a very good selectivity towards structural isomers, as can be seen here. So the selectivity is also very different compared to classical silica-based materials. Now, temperature, we operated the system at slightly elevated temperature, 60 degrees. This is always beneficial to reduce the huge viscosity or pressure maximum you observe after running a solvent gradient. And this is also the reason why we used mixtures of water and methanol in the first dimension, because this is not the pressure critical separation. The second dimension we really need to optimize in terms of speed, and therefore we used acetonitrile water, which is a much lower viscosity maximum during the solvent gradient. You can also see the flow rates we used, 200 nanoliters per minute in the first dimension, 40 microliter per minute in the second dimension, as I showed you before. No, generally elevated temperature leads to reducing the viscosity maximum. Now, when it comes to the injection volume, it's very critical because you have to make sure that if you inject a sample, you will detect some peaks. So we have to make a large volume injection on the first dimension column. And in this dimension, 1.5 microliter is already a very large volume injection. I will show you the effect if you just increase the injection volume on a conventional RP-C18 stationary phase, so 50 nanoliters would be optimal. If we just increase the injection volume up to 1000 nanoliter, you see that the peak here completely deteriorates. So this compound was a dead time marker in classical RP-C18 chemistry. And you see that just increasing the injection volume will not help to increase the limit of detection. So if we just instead use the PGC column, you can see that clear peak focusing is possible even for compounds which are not retained on classical C18 materials. And we can increase the injection volume up to 2000 nanoliter without any peak deterioration. Okay, gradient programming in this case was kept very simple. So for the nano LC dimension, we used a very long linear gradient with an isocratic plateau at the end. And for the second dimension, we programmed cycle times of about 1 minute, which you can see here. So every minute, one cycle time in the second dimension is run. So in effect, it's very easy. Okay, then I come to the measurement of the reference standard, where we used everything we had in the laboratory, substances which play a role in environmental screening analysis, from radio contrast agencies to beta blockers, cytostatics, and so on. And this reference standard has a very high concentration, 1 milligram per liter, to make sure that the system is really working. And it contained 162 compounds, as you can see here. Now, this is a typical total ion current chromatogram of this reference standard and 2D LC. You see here on the y-axis retention time for the second dimension, it's just 1 minute. And here on the x-axis, this is in some way correlated to the retention time. It's the D1 fraction number. I see we have a very long runtime of about 100 minutes. What you can already observe here is that in some areas we have really a high degree of orthogonality. So we would have complete coelution for these substances in D1, beautiful separation in D2, and also the same for the second dimension where we have a coelution here, we have a very nice separation in D2. So this underlines that selectivity differences are great enough to make two-dimensional separation work. Unfortunately, a tick is not very useful, so what we created here is the Analyte map on the base of the reference standard, where you can see how the substances spread over the available chromatographic space. We also calculated the orthogonality for the system, which was estimated to 0.61, which was according to a convex hull, which is not that bad. And we can see here in detail, as I showed you, that we have complete coelution on D1, a beautiful separation in D2. And this is what you might be interested in. I will show you now a typical chromatogram we obtain on the second dimension for these Analyte peaks I marked here. And the respective chromatogram is shown here. And I think it's really a beautiful separation. So from the first to the last eluting compounds, it's just 18 seconds. Peak width are about 1 to 2 seconds. So in this case, we already achieved baseline separation of these compounds. Very, very nice. It's something about the retention time stability in second dimension for one compound. And what you can see here is that for every fraction we take, the difference is in the third decimal, after the third decimal point. So deviation in D2 is just between 0.01 and 0.002 minutes, which translates to a deviation of less than 0.6 seconds. I think this is really brilliant for micro-LC, and it underlines that micro-LC is really a robust technique. Okay, coming now to the application. So some of our projects are dealing with investigating new technologies for optimization of wastewater treatment plants. So as you might have heard, many organic micropollutants are not sufficiently removed by conventional treatment processes. And therefore, new technologies will be evaluated. One of them is advanced oxidation processes. It's ozonation. And this picture is not that up to date. So on this side, an ozonation plant has been built to study the degradation effect of ozonation. But this was not important for us. We liked a sample with a high matrix load. So a sample was collected from the influent to the wastewater treatment plant. Now, and this is the respective total ion current chromatogram of this wastewater sample. And you see we have a huge peak density here, and you see a similar picture like I showed you before from the reference standard. And peaks are really nicely separated here above the two-dimensional chromatographic space. Now, this is the Analyte map created on basis of the suspect screening we performed. And with this approach, we were able to detect approximately 60 compounds, or identify 60 compounds in this wastewater sample. Now, I show you here a very nice example. What makes it clear, it's a good idea to have MS functionalities. So what you see here is the XIC chromatogram for this extracted mass, and what clearly strikes is that we have two distinct peak maxima for the same mass. So this might appear that there is a split peak in the first dimension, hinting at probably bad chromatographic conditions. But what is, if we look at the MS information, and we've done this using the information-dependent acquisition, and we acquired some product ion spectra here at the peaks I just marked. Now, what you see here is the product ion spectra for the same precursor ion, but at different retention times. So here for 1.32 minutes, here for 3.32 minutes, just two more fractions. And what we can clearly see is that the product ion spectra are different. Now we have performing a suspect screening, which is based on our reference list, and we know what might there in the sample. So we have here some structural isomers, ifosfamide and cyclophosphamide. We can also assign these mass fragments to the structure and can, with this approach, clearly identify the substances. So it is really a great feature. So the availability of MS spectra really helps to clearly identify compounds, even when there is a complete coelution in the second dimension. Okay, this brings me to the solvent consumption in nano or capillary liquid chromatography. I plotted here some figures of merit. So the inner diameters of columns for let's say classical HPLC or UHPLC systems. So as you might know, Waters promotes their new I-class system, can also be used with columns with an internal diameter of 1 millimeter, while true nano LC is between, let's say, 25 and 100 micrometer ID, and capillary or micro LCs from 0.1 to 1 millimeter ID. In fact, you can use all particle sizes with all combinations. Well, if we look at the flow rate for the different approaches, if we are doing conventional HPLC MS hyphenation and electrospray ionization, usually optimum is around 300 microliters per minute. If you use the, I have called it conventional LC times LC approach, which is often described in the literature, in order to get very fast separations in the second dimension, flow rate is up to 5 milliliter per minute. While in our approach, we are somewhere between 40 and 50 microliter per minute. So if you look at the solvent consumption just for your conventional LC MS hyphenation, it's just half a liter per 24 hours. And if we go to this conventional LC times LC approach, 7 liters are consumed within 24 hours. Whereas in our approach for the micro LC, just 72 microliters are consumed. So it's really very, very low, and I think it's one of the major benefits of these miniaturized techniques. Okay, so overall solvent consumption can be really reduced. Now this directly leads me to my conclusions. Just go through it. Our multidimensional system is made up of an online LC times LC approach. Of course, there is the possibility to make offline LC, but this is very, very time consuming. In the first dimension, we used a nano LC column based on porous graphitic carbon. This is very, very important to make a large volume injection, especially on the first dimension column. In the second dimension, we used a core shell stationary phase based on classical silica C18 chemistry. It's a micro LC UHPLC column, which is stable up to a pressure of 1000 bar. The complete system is run at 60 degrees for both dimensions to reduce the pressure, and which leads to lower viscosity maxima during the solvent gradients. With this approach, we have an overall splitless design, so there is no flow splitting at the pumps, there is no flow splitters when we connect the column to the mass spectrometer. And in order to have a very good identification, we use hybrid high-resolution MS detection. Well, these components make up the multidimensional system we have developed on the basis of the Eksigent platform, I would call it. And I would now like to come to the outlook to discuss some issues which have to be implemented, which have to be resolved. And one of it is clearly the software implementation for LC times LC. So there are many vendors or manufacturers which have now their systems on the market. It's Agilent, it's Shimadzu, and the problem is always that you need very good software for data processing. Now, what are the steps you need? So I've marked this here. So first of all, you have the sampling of the first dimension Analyte, which means you make your modulation. This means, as you can see here, you collect several fractions over your peak, which is called the modulation. Actually, the detector only sees one raw data file, so there's a consecutive data acquisition by the detector in one raw data file. And then we have to make a rearrangement of the single D2 chromatograms to a matrix, so that we have this two-dimensional plot I've shown you before with the retention time of first dimension, retention time of second dimension, and of course the intensity. And yeah, we had to do this on ourselves because there was no software available at the moment, so this is very, very time consuming, of course. And the last step is then clearly the visualization as either a 2D plot or 3D plot, and to work with it. Fortunately, there is a cooperation with the company GC Image, which is it's a spin-off of the University of Nebraska. Its founder is Professor Steve Reichenbach, who is very experienced in programming software for multidimensional separations, including GC times GC, but also for other manufacturers like Eksigent Ultra. We had this cooperation, and we also used some test data from our sample and loaded it in the software, and I think we are quite happily because they told us that in the next month there will be a commercially available software solution for LC times LC data analysis provided on the ABSykes platform. So of course there are other fields of applications for LC times LC. If you're a little bit familiar with this technique, it is very strong in the field of polymer analysis, so especially the group of Professor Schoonmakers of University of Amsterdam have used this technique, I think 10 or 20 years ago for polymer analysis, where usually combine size exclusion or gel permeation chromatography with reverse phase chromatography, so it's very well established. In food analysis, well, it's mainly dominated by GC times GC, but I think with the availability of the respective LC times LC systems, it's also possible to make a complex screening here. And I've shown you the workflow for the environmental screening. Well, I think this is quite new because before no one has used this kind of system for environmental screening. And of course, pharmaceutical analysis is a little bit different, so the workflow is more of a hard-cutting technique. If you want to assess the purity of your active pharmaceutical ingredient, you usually only transfer one fraction of your chromatogram to another column to run a separation there to make sure that the peak is really clean. So in this aspect, it's more the hard-cutting approach which is used and not the comprehensive mode. Of course, if you want to apply the system to other applications, it is necessary to adapt the phase system to the sample, which means you have to think of the orthogonality of your phase system. So many authors used normal phase columns or Hill columns in the first dimension, and reverse phase columns in the second dimension, which have also very good orthogonality. So this is not that straightforward, and I think this is also very demanding, that we need to invest more time to assist the users if they want to use the system in different fields of application. Okay, with this I come to the acknowledgements. I would like to acknowledge some people which have supported us. So first of all, there is Michael Schlüsener, Thomas Tanners, for the possibility to use their ABSykes triple top instrument. Then there is Hagen Breik-Steiner from Vichy, great support about valve technology, because the first system we used was delivered with Weodyne valves, and we had really some problems because you have many modulation steps within one chromatographic run. So if you have a method of 100 minutes and your cycle time is 1 minute, the valve switches about 100 times during this time. And the system is operated at elevated temperature, and we are going to the pressure limit of the system, so it's run about 600-650 bars. We're now quite happy with the new valves. Also, Jürgen Meyer-Rosenkranz from Grace, because one of the problems which is always encountered if you want to use micro LC is that the respective column formats are not available by the original vendors. But they are able to repack everything in every hardware you would like to use. So great support from their side, and thank you very much. So with this, I'm at the end of my talk. I thank you for your attention. I hope it was interesting. And yeah, if there are any questions, I hope I can answer them. Okay, thank you very much.
Super, that was excellent. Thank you very, very much, Torsten, for the very clear presentation. We have a few questions which have come in during the presentation. Super. Thank you, everyone, for filling in the questionnaire. It's really important for us as a company to gauge your feedback and to allow us to select webinars for the future. Torsten, I'd like to now just to ask you a few questions which are coming from the listeners, if that's okay.
Yeah.
The first one which came from was, could you explain the reason behind the higher loadability on the PGC column, please?
Okay. Yeah, actually, the reason is that for the polar components, which are very important in environmental water analysis, we need a column with a high retentivity. So the example I showed, I mentioned that the test compounds we used were compounds which are not retained on a silica-based C18 stationary phase. So this means they are eluting with a dead time. So in this respect, I need a column which is able to retain my compound, and this will mean that I can inject a higher sample volume in order to increase the limit of detection. So in this respect, it has nothing to do with, let's say, the loadability. It's an effect of retentivity. So you need to find the right column to retain your compounds. In effect, this is really a problem if you would like to make a comparison between a 1D approach and a 2D LC approach. So let me elaborate on this, because I think this is very important. If you look at some talks about LC times LC, the question about the sample volume or injection volume which will be introduced on your system is always never be answered. So we are interested in identifying as many compounds as we can with these screening approaches, and what we are currently working on is that we try to make a comparison between a classical one-dimensional LC-MS screening approach people are using, for instance, conventional analytical columns of 2.1 millimeter ID, conventional LC equipment with our approach. And it is very interesting, so that the first results show that with this system we can not only compete with the classical approaches, we are a little bit better, and interestingly, we see different columns, compounds with our approach than with the classical 1D LC approach. I think we will publish the data within the next few months, and this was the main reason why we used a PGC column in the first dimension. There is a publication by the group of Peter Carr, who have also developed an LC times LC system. They use the higher retentive column in the second dimension to get rid of this problem when you transfer organic solvent on your second column, that you have peak distortion. But it clearly depends on the field of application, what I also showed at the end of the presentation. So this is really a detrimental step. I hope the question is answered.
Super. Thanks, Torsten. Before I go on to the next question, I'd like to remind everybody that these webinars can be downloaded and viewed again. They'll be available on the Eksigent website, so by all means you can get access to these webinars after the event. We have two more questions. So we'll just flip on to the next one. The next one's from Gerard. When transferring the first portion of D1 onto D2 and elute D2 into the mass spec, what happened to the next D1 portion?
Okay, I know this is a question which is often asked, and I know the most critical step in understanding is this modulation process. In effect, our system is an online system, so we do not stop the flow. So while the second, while D2, the second fraction is going into the MS, we have a constant elution from the D1 column, and we use the other sample loop I've shown in this modulation scheme for sample storage. So this means we have a continuous filling of the other loop, while the other is connected to the second dimension column. So I think what many people are worried about is the fact that we need to have at least 3 to 4 cuts over a chromatographic peak. The reason is that if we only do this in one fraction, we completely lose the resolution we already gained on the first dimension column. So this is based on the MSF criterion, which was developed by Murphy, Foley, and Shuri. And yeah, this is something which is really critical. So the peaks, in effect, are really broad on the first dimension, but this is not a real problem because we fractionate the peak and then analyze these portion of the peaks on the D2 column. Of course, if you would only take one sample over the peak, our peak might be undersampled, and then we completely lose the resolution we have already gained on the first dimension column. So this means if you use a UHPLC column in D1 and you create peak width of about, let's say, 5 to 10 seconds, it will not be possible to use LC times LC in this respect.
Yeah, that makes perfect sense to me. And the final question we have is that I know you talk about using different stationary phases here when you use your column switching, but have you tried normal versus reverse phase for the second dimension, or sort of a polarity switch? This is put forward by Debasis.
Yeah, so we have tried to really make the system suitable for the environmental water screening. Of course, if we just use other columns or make this polarity switch, there are clearly other selectivities. In our lab, we didn't use the system in another way because, as I explained earlier, we need a high retentive column in D1. But of course, it would have some advantages if we could use the PGC phase in D2, because then we might even inject a much higher transfer volume from the first to the second column. So definitely there are differences in selectivity, but it always depends on your sample. And if you have, let's say, an SPE extract, catcher's extract from, let's say, a T extract or so, it might be a very good idea to use a normal phase, a helic phase in the first dimension, because this would then be compatible with the high organic load of your SPE cartridge. And then you have the reverse phase in the second dimension. So it clearly depends on your application and if you're doing SPE for pre-concentration or so.
Thank you, Torsten, for asking that question. That was the last in the list of questions I saw from the webinar. Again, I would like to thank Torsten for his very clear presentation today and giving us the time to answer the questions at the end of the talk. I would like to thank everyone for attending the webinar. Please look at our series. There are more occurring, especially in the pharmaceutical area. I know there's a request for looking at micro-LC in the pharmaceutical area moving forward. Again, thank you very much, Torsten, and goodbye to everyone today.